everyone. Today let us talk about real-time anomaly detection with autoencoders. Real-time anomaly detection involves identifying unusual patterns or events as they happen in live data streams. Now, what is an anomaly? Anything technically that is not normal or weirdly abnormal can be, anything unusual, right, can be identified as an anomaly in the data. Now, anomalies can indicate critical issues like fraud, system failures, or cyber attacks. So, spotting them early prevents costly damages. So, this is crucial for these kind of fields where you have frauds happening or you have security issues, security threats, and system monitoring that needs to be frequently done. In those cases, anomaly detection helps us, plan contingencies. So this helps organizations respond to threats and prevent failures proactively. Now, what are autoencoders and what role do they have to play here? Autoencoders are neural networks that learn to compress and reconstruct data from the normal data that is used to train them. So this neural network is designed to learn efficient data representations. Now it contains two parts, encoder and decoder. Encoder compresses the input data into small latent space, while decoder reconstructs the original input from the compressed representation. So first from the data, it encodes and then the output is again decoded to reconstruct the data. Now, this basic structure of autoencoder is trained based on the regular patterns of data such that the difference or the reconstruction error, the difference between the reconstructed input and the actual input is minimized. So the whole neural network is trained on the normal data to minimize the reconstruction error between the reconstructed input after encoding and decoding phase and original data, correct? Now, because this neural net model is trained on the original data, which is normal, now autoencoders cannot do this reconstruction effectively for anomalous data. And that is what we use to use these autoencoders for. That aspect of this autoencoders is used for anomaly detection. Now, in real time, how this works is, so you train the autoencoder on normal data. Now, because of that, the autoencoder learns the normal pattern characteristics too well, and any data that is normal will be instantly encoded, decoded, and if you see the reconstructed pattern, it will be exactly or, almost matching the original data. In this training process, because it is only exposed to normal patterns, right? The moment, so this is called your detection phase. You feed the live streaming data to the trained autoencoder and you keep calculating the reconstruction error. Because this is a model trained to minimize the reconstruction error, on as long as the input data is again normal, the reconstruction error will be minimum. Now, if the reconstruction error is high, it means it is trying to reconstruct something that it has not seen before. If your data is like this, because it is trained on data like this is like training data. This is your live data. So this kind of data, it can obviously reconstruct correctly. Now, for example, in the live stream, you have a data like this, a spike, right? A single spike. Now, what happens? That data, in the process of reconstruction, it will still try to reconstruct, but the spike will not be reconstructed fully. If you have a spike like this, the reconstruction may only happen like this. So the reconstruction error, the difference between the actual and live, will be maximum, or the moment the reconstruction error is beyond some value, you can say that the data is anomalous because my autoencoder is failing to reconstruct the data, right? So this aspect of efficient reconstructive ability of autoencoders is used for anomaly detection by making sure that if there is high reconstruction error, it means that the data is possibly anomalous. It is potentially anomalous data, right? The benefits of using autoencoders in this kind of anomaly detection is it can handle high dimensional complex data without any feature engineering techniques. It is very fast and scalable and hence suitable for real-time monitoring systems. Now, it also reduces false positives compared to the traditional rule-based methods, right? Now, let us see the implementation of this in Google Colab, right? I'm sharing my Colab screen where I'm creating a small data using libraries where the data is normal and it will automatically reconstruct the data. So I import my necessary libraries and using numerical Python sign function, I create a data. Using a random function, I add little randomness to this data. So normal data is also supposed to have some certain element of normalcy. Certain element of randomness, correct? So accordingly, using random function, I add slightly a little bit of randomness to the data. And if you look at my data, give it a minute. All the libraries are getting imported. So this is how my data is going to be. Correct? A two-dimensional array of the shape -1. -1 indicates it depends on how many rows are there, right? A two-dimensional vector is created. Now, next we go. I build a so simple autoencoder using neural network, correct? Right? So I build an encoder as well as decoder using dense layers of neural networks, giving ReLU as activation function. And I design a model which has its input layer and then the decoded output as the output, right? Now I compile this model and I fit my normal data to it, correct? So here my input data is also X normal and the target ideal data is also X normal because it's going to encode and decode the same data and compare it with the original same data, correct? So that way, when I try to do it, when I try to build a simple autoencoder, and then now my encoder is trained with normal data. Now what I'm trying to do here is I'm generating a test data in the same way I generated the test data. I generated the training data. At the same time, I am injecting an anomaly in specific location using the slice path. Right? The sine wave must have a value of -1 to +1, while from the range 250 to 260, I'm including a value of 3, which is technically an anomaly. Now, I use the autoencoder to reconstruct the test data. And if you see the reconstruction error along with a small threshold value, if the threshold is larger than this, then we call it anomalies. So this is how I define it, correct? Now, the way you see reconstruction error may not be efficient, but if you can plot them and see using matplotlib, you see that this has been the original data and the reconstructed data is with orange color. If you see everywhere, it is properly overlapped except in some corners almost where you can say that it is zero error. Now this part is when the peak part of the original data in blue color, when you reconstruct it, there is a difference. Now this difference is not there in the regular pattern. It is only observed in this anomaly because the model is trained to regular data. It knows how to reconstruct the regular data very well. So this difference is compared with the threshold, and if the threshold is large, you mark it as anomaly, right? So this is what your autoencoder does to do anomaly detection, right? So in this way, you can use autoencoders for anomaly detection. Now, use cases. So these kind of things, these kind of autoencoders for anomaly detection are used in network intrusion detection, where you have abnormal traffic patterns. You use it in predictive maintenance. You also use it in healthcare monitoring, where you flag unusual patient vitals or sensor readings. Similarly, to identify fraudulent transactions in finance fields. So the use cases are, the list of use cases is endless. So to conclude, autoencoders provide a robust, scalable approach for real-time anomaly detection. It enables organizations to detect and address issues before they escalate. And hence, it proves to be a critical tool for maintaining security, reliability, and operational efficiency of the system. So this is the end of real-time anomaly detection with autoencoders. Thank you so much.